So this is the last lesson that is relevant to the first test. So Monday will be a review. Really, I'm going to go over the practice solution, and so there'll be time to ask any questions about that or to give our material. And then Wednesday, the day the test is posted, there will not be class. Of course, there will also not be class the following Monday because of Mardi Gras break. So you get a bit of time off in a way. So. Okay. So continuing with the Fourier transform. So I've shown how to use the Fourier transform to solve a PDE. You need to take the Fourier transform of the PDE itself, which means knowing how to transform derivatives of functions. You also need to take the transform of your initial data. So what's involved with that depends on the kind of functions you have. So we're going to look at certain properties that make it possible to take Fourier transforms of at least certain kinds of functions. Okay. So here's some basic properties of the Fourier transform and its inverse. So first, if you have a function little f of x, and you take its Fourier transform, which gives you a new function, capital F of xc, where xc is the variable in frequency space, then the inverse transform applied to capital F really does give you back little f of x. So what's happening here is, here in the square brackets, you're taking the Fourier transform of little f of y, and that becomes capital F of xc right here. Then over here, you're taking the inverse transform of capital F, you see, that brings you back to little f. So in other words, this fancy f here denotes Fourier transform. So the inverse of Fourier transform brings you back to f. There's a cancellation effect there. Next property, like many operations we come across, Fourier transform is a linear operation. So, in other words, the Fourier transform of a sum of functions is the sum of their Fourier transforms. If you scale a function by a constant, then the Fourier transform is scaled by that same constant. And all of that is encapsulated in this statement right here, that Fourier transform of a linear combination of functions f and g, where alpha and beta are the coefficients of the linear combination, is the same linear combination of the Fourier transforms of f and g individually. So, so a practical consequence of that when solving PDEs is, I suppose your initial data is a sum of functions, you can transform them individually and add the transforms together. This next one is particularly important for solving PDEs with Fourier transform, the derivative. So, so here we're taking a Fourier transform of f prime. We'd like to be able to express the transform of f prime in terms of the transform of f. Because presumably we would, the transform of f might be something that we're solving for or something we already know how to get. So to show you what's happening here, I'm applying the definition of the Fourier transform to f prime. Then what I do is apply integration by parts. So if f prime is playing a role in the dv, and then e to the minus ixx is playing a role in the u in the integration by parts formula, then we have a boundary terms that come about from integration by parts, and then we'll have this integral. So this is the integral of a v du part. Now the boundary terms, for a Fourier transform to be well defined for a function little f, there are some assumptions. I'm not getting into the technical details, except certainly f would have to be integrable over the entire real number line. from minus infinity to infinity. And that would necessitate that little f must go to 0 as x goes to plus or minus infinity. So for that reason, the boundary terms will end up being 0. And then what's left over here? Well, I have this factor IC that comes from taking a derivative of e to the minus ICX. And then everything that's left here fits exactly the definition of the Fourier transform of little f. So I can replace this entire integral, including the 1 over square root of 2 pi scaling factor, with Fourier transform of f. So what we see here, the final result, is a very simple relationship between Fourier transform of a function and that of its derivative. And all you're doing is, to get the transform of derivative, you take the transform of the original function, and you multiply that by IC. And that just stems from the fact that the derivative of the function e to the ICX with respect to x is itself times IC. So that's where this comes from. Then certainly you can see, you can apply this repeatedly. For example, Fourier transform of a second derivative would be minus c squared times the Fourier transform of the original. So questions about the first few properties?
Oh, you said the first term like equals 0 because it cancels out?
It's because it's really what you're doing, you're taking the limit of this part as x goes to plus or minus infinity. And we're assuming here that f is the kind of function that does go to 0 at both ends, because otherwise the Fourier transform of f cannot be taken. Okay, here's what I just mentioned about the second derivative, that is just applying this twice. And this is something that comes up often in, for example, in solving the heat equation using a Fourier transform. But I want to emphasize, the Fourier transform is applied to a function of x. And that's where, so this property applies for differentiation with respect to that same variable x. If a function happens to depend on other variables like t, the Fourier transform does not affect those. So therefore, for derivatives, the differentiation in respect to t just passes through a transform. So here, if I know that the Fourier transform of little u is capital U, and then I want to know what the Fourier transform of derivative of u, little u with respect to t, I'm going to take a derivative of a transform with respect to t. So, so whereas the Laplace transform is normally applied to functions of time, Fourier transform is applied to functions of space. So other variables are just ignored in a way. Okay, now, I did mention earlier that the Fourier transform of a sum is the sum of the transforms, and you're used to a similar property for derivatives. But you also know for derivatives, the derivative of a product is not the product of derivatives. You have a product rule. Here too, the Fourier transform of a product is not the product of the transforms. So it's a rather unusual operation that applies instead. So I'll show you what happens here. Suppose I have two functions, little f, little g. I take their Fourier transforms individually, and I multiply the transforms together, and then I want to go back, take the inverse transform. So what happens in that case? So here, I've just applied the definition of the inverse Fourier transform to a product, capital F. So I'm using capital F to refer to transform of little f, capital G is a transform of little g. So the same convention I've been using. And then what I do, to try to figure out what this is, I rewrite capital G in terms of little g. So capital G is a Fourier transform of little g, so that's what's in the square brackets here. Then what I do is I rearrange the order of integration. Because here I have y, inner integrals with respect to y, outer integrals with respect to c. Now I switch the order of integration. So capital F goes inside, but I leave the exponential e to the minus ixy here, and I take this exponential e to the ixx, and I have to move that inside now. So the exponentials are now combined. And then I have g of y sitting here. Now, what's in the square brackets here is the definition of inverse Fourier transform applied to capital F. But look at the exponent here, e to the ixy x minus y. Now, normally with the inverse transform, we have something like this, where we have e to the ixy x, and the result of this is a function of x. Well, here, in place of x, we have the quantity x minus y. So this whole expression, yeah, we are taking inverse transform of capital F, but the result is not going to be little f of x. It's going to be little f of what we have here, x minus y. And that's what lines up here. And then the g of y was already sitting here. So this is what we get. So we're able to express the inverse transform of a transforms of little f and little g in terms of little f and little g, but it's this operation that's applied to them. And this is called the convolution of f and g. And this is one way of writing it. So f star g, not to be confused with multiplication. F star g, and results as a function of x, because which is what the inverse transform is supposed to be. Because here we have f of x minus y times g of y, and we're integrating that from minus infinity to infinity with respect to y. So y is taken up by the integral. The result of this whole integral depends on x. So, and here's the definition of the convolution operation. Common application of convolutions is smoothing. So if you have a function that has a lot of sharp features to it, high frequency oscillations, jump discontinuity, things like that, you can take its convolution with of some function and get a smoothed out version of the original. Okay, so here's the rule that we have, that the transform of a convolution is a product of the transforms. So really, this is another way of writing, if I take this result, f inverse of f little f, f little g is equal to this, and now I take the Fourier transform of both sides of this equation, that would cancel out the fancy f inverse over here, and this rule pops out. So the product of the transforms is a transform of a convolution. Okay, here's an example of convolution. So little f equals fxx, g of x is a Gaussian function, e to the minus x squared. So what I end up getting in this case is so here I have the definition of convolution, where I have the first function evaluated at x minus y, and then the other function is evaluated at y. Okay. And what ends up happening here is I can break this up into two integrals. First is x times e to the minus y squared, which is what we see here. And then we have minus integral of y times e to the minus y squared. the integral of y e to the minus y squared, that can be handled using a u substitution. And it actually can be shown that the integral of that part turns out to be 0. So the y part ends up disappearing, and this is what's left. Okay, and actually that's what I use here. And here, this integral from minus infinity to infinity of the Gaussian function, this is not something that can be evaluated by normal means because there is no known antiderivative of a Gaussian function. But it's known that the value of this integral is the square root of pi. So, we end up getting x over square root of 2 for a final result. Questions about this example? All right. Now, why we need Fourier transforms, of course, is to solve PDEs. Now, for a Fourier transform we've just been showing you that involves integrals from minus infinity to infinity, you would use them to solve a PDE that's defined on minus infinity to infinity. Therefore, there are no boundary conditions. So we're not solving an IVDP like we have been. It's just an IVP, or initial value problem, also known as a Cauchy problem. So all you have is a PDE like this one, and some initial condition. So how you go about solving this is you need to take the Fourier transform of both a PDE and the initial condition. So when you take the transform of the PDE versus from a time derivative, the transform of the time derivative is just a time derivative of a transform. So the idea is we let capital U be the Fourier transform of little u, and differentiation with respect to t just passes through. On the other side, alpha squared is a constant, so I'll just stick around. The transform of a derivative with respect to x, because it's a second derivative, we're going to take the transform of the original, that's for the capital U here, multiplied by the quantity ic squared, which turns out to be minus 6c squared. So that's what leads to this factor here. And then for the initial condition, transform both sides of this. So we're going to have the transform of the solution evaluated at t equals 0 on the left side. And then whatever the transform of this is, that's what's going to go on the right side. So what you have as a result of this, if you put these two together, you again have an initial value problem, but for an ODE rather than a PDE. So here we have our ODE, and you can think of C as a parameter. You can think of like it being an unknown constant. But this is an ODE, just one variable, t. And here's the initial condition for that ODE. Now this kind of ODE, we know how to solve. Because when you have the ODE, the time derivative is equal to a constant times itself, then the solution is going to be the exponential with this constant times t, and then what's multiplying it is the initial value. I'm going to go ahead and add that in here. Something that comes up often enough. So again, like y prime equals ky, y of 0 equals y naught. That's the initial value problem. The solution is y of t is y naught, the initial value, times e to the kt, for whatever constant k you have here. So this initial value problem is nothing more than an example of this initial value problem, and we're applying this solution formula. And now we have the Fourier transform of the solution. Are there questions up to this point? The only thing left is to take the inverse transform of this, and then we'll have our solution. Now, so little u is the inverse transform of big U. We fill in what big U is. But here we have the inverse transform of a product. Well, that would be the convolution of the inverse transforms of these two factors individually. And the reason I'm thinking of it that way is we know what the inverse transform of capital phi is, capital phi bc. The inverse transform of that is little phi of x, because that's just a transform of our initial data. So we like to express our solution in terms of the initial data that we're given. Now, what about the transform of this? So that's actually known. But it's equal to this, and I'll talk about that more a little bit later on. But now, to express the convolution of this, we would use the formula for convolution that was given earlier. Okay, so the convolution formula is you have 1 over square root of 2 pi out front, integral from minus infinity to infinity. One of these functions is evaluated at x minus y, the other is evaluated at y. Due to symmetry, that it doesn't matter which one, the convolution is commutative. So then if I apply that down here, so I have 1 over square root of 2 pi as part of this, and then I'll have this constant factor that I'll put up front and combine it from 1 over square root of 2 pi. And that gives me this constant factor here. Okay, integral from minus infinity to infinity. This function evaluated at y, and then the other function involved evaluated at x minus y. And here we have, as much as possible, our solution. So it's generally not possible, except in certain special cases, to actually evaluate this integral, mainly because there's a Gaussian function involved. So we have to settle for this solution being in integral form. And like I said, on the test, on the real test, I'll make sure to indicate whether it's okay, just leave the answer as an integral. But I don't want you spending time evaluating an integral, especially if it turns out to be impossible, like this one would be. Okay. So this would serve as the final answer. A way to interpret this integral is, because if t was equal to 0, this integral would turn out to be just phi of x. But for t greater than 0, in a way what's happening is the content of phi of x is being smeared all over real number line. And which is what you would expect physically, because suppose your initial temperature profile is, let's say the temperature is 0 throughout the domain, except for at one place you have a heat source. So then you have like a spike at some point, let's say at x equals 0, where there's heat. Well, over time, that heat is going to spread all over the domain. Temperature diffuses. So the solution will smooth out, eventually converge to some constant temperature. And that's what I mentioned what convolution does. It has the effect of smoothing the functions involved. Now, as far as the inverse transform is concerned, all right. I need to share something else here so you can see the whole process. Okay. I'm gonna unshare and reshare. Okay, need to pull something from the book. All right, 1 second. Okay. Now, in the back of the book, there are several tables of Fourier transforms that will be of use to you for certain problems. Okay, so here are the integral transform tables. It's important to pay attention to the formulas at the top of each table so you can make sure you're using the right table for whatever transform you're doing. So for this problem, it's this table, table A, that we want to use. So the left column has functions of x, and then the right column has their Fourier transforms. So when you want to take a transform of a function or inverse transform, you look at the appropriate column and figure out which one of these rules fits your function. So in this case, we want to take the inverse function, inverse transform of some Gaussian function. Now we have a lot of constant factors in here. We have this like 4 alpha squared in the denominator. We have a t in the denominator also. Now t is a variable, but Fourier transforms operate on functions of x. So in that setting, you can think of t also as a constant, just like as some fixed value. So I want to find a Fourier transform rule that fits a Gaussian function. To show you how we got from this all the way to this. So if I look at the table, I'm looking for either in this column a Gaussian function of x, or in this column a Gaussian function of xc. And let's see what we get. And here it is. It's a little bigger. All right, so we have e to the minus a squared x squared is a function of x. You take the Fourier transform of it, and you get this function. Now here, the Fourier variable we're using in the table is omega. That corresponds to our xc. So what I've done in the notes is I've copied down this rule. This is the appropriate change in notation. And that's what I have here. So this is exactly that rule, that the inverse transform of this function gives you this one, where the constant a here is the same constant a over here. And the thing is, I want to find a way to fit this rule to my situation. So the thing is, so based from what the table tells me, if I have this function, I know what the inverse transform is. It's e to the minus a squared x squared. But I don't have this. I have this, e to the minus alpha squared c squared t. So I have the exponentials corresponding. I have the minus xc squared corresponding. But where my constant scaling factor here is alpha squared t, that has to match up with the constant scaling factor here, which is 1 over 4a squared. So what I do is I match these up. I say, okay, I have some constant alpha here, I have some constant a here, that can be equal to whatever I need it to be to make this work. So by matching this, setting this expression and this expression equal to each other, and canceling things out, like a minus 6c squared would cancel out. And what am I left with? This. This is the key right here. So by seeing that these are equal from setting this exponent and this exponent equal to each other, I can solve this for my unknown constant alpha. Actually, no, sorry, not alpha, A. The A in this rule is what I want to solve for. So I go ahead and solve for it. And that means whatever expression I get for A, I can substitute here into the inverse transform. And that's what I've done. So, because notice we have 1 over A square root of 2 multiplying this. So this expression I fill in for A here and here. So, okay. Now, so really what you see here is this rule exactly with the now known value of A filled in. Here and here. And then everything else I do like to this point, I just simplify that. And I also simplify plugging A in over here too. And this is what I get. So then, now, the other thing I need to point out though is by simplifying this as much as I can, I find that the inverse transform of this is equal to the exponential. But what am I inverse transforming? I'm not actually inverse transforming this. I'm inverse transforming only this, just the exponential by itself. As for the scaling factor, I just divide. So now I move this to the other side, which is how it shows up out here. So this is what you can do to make a Fourier transform rule from your table fit the situation that you're dealing with. So it means whatever unknown parameters are in the rule from the table, you have to figure out what they should be in your situation. Also, you all certainly have to move constant factors from one side of the equation to the other to make it an exact fit. Because since this is what I want to transform, I find the value of A that lets me apply this rule, and then move this scaling factor to the other side, so that the only thing I'm inverse transforming is this exponential function. That's what I have here. So algebraically, you gotta proceed carefully. So questions about how this inversion was performed? Let me make some notes in here about what happened. This fleshes out a little more carefully clearly what happened here. That this is transform I needed, and all this work up here helped me figure out what that is. One way to interpret this solution formula that we have here is convolution of your initial data with this Gaussian function. So that exponential is also known as the impulse response function, also known as a Green's function. So to figure out the temperature at any point along the real number line at any particular time, you can think of it as taking, for each other point along the real number line y, you're determining what is the response at x to the impulse at y. And the Green's function tells you what that response will be. So really, you think of the Green's function as mapping an impulse to a response. And the collection of all those responses is your solution at that point. And because what happens is, the property of solutions to the heat equation is even if the initial data is zero just about everywhere, except at one small interval, the solution to the heat equation, once time moves forward the smallest amount, the solution can be non-zero everywhere immediately. It's called infinite speed of propagation. And now, for initial data like that, if you're far away from where that initial data is non-zero, and only a short amount of time has passed, the effect won't be very much, naturally, but there is something. And that this impulse response function has the effect of quantifying the effect of a heat source at one point on an observer at another point. So that's what this formula reflects, is at a given point x and a given time t, what is the effect of a stimulus or heat source at y at some point in space-time elsewhere. So, questions about any of this, or homework questions?
Actually, I have a question about way back homework 1.
Oh, okay.
So going by the book and the notes have different proofs, and so I was trying to go by I tried going by the notes proofs, and I was also trying to go by the book's proofs. The problem I get is that I end up with...
Which problem?
This is lesson 4, problem 4. Where you have to derive the heat equation using k as a function of x. And
lesson 4, problem 3.
Yeah, sorry.
Yeah.
That might. And what I go with the mean value theorem, and what I end up with is I still end up with k of xe outside of the parentheses.
Because what's happening is that k should never be outside of parentheses in the first place. In this situation here, yes, but not when k is a function of x, you don't get k out here.
Right.
You'll have k of x plus delta x multiplying this,
Okay,
and then just plain old k of x multiplying this.
I see. Okay.
Yeah.
And so you can kind of think of k of x plus delta x
Yes.
as as times u, partial derivative of u with respect to x.
Yeah.
Of k plus delta x. You can kind of think of that as one function, right?
Yeah, and then actually, that is how you need to think of it in this situation.
Right, because because you use the definition of derivative too.
Right.
Okay.
Yeah, and really, in both cases, k constant, k not constant, k times ux is what's being differentiated. It's just that in the first case, k is a constant, so it doesn't really affect anything you pull it out.
Okay, and you can pull it out. Is that because it's a derivative, or I mean, an integral? So you can pull it out of an integral.
Yeah, so those whatever constant multiple rules apply in this case. But once k starts depending on x, then no longer applies.
Okay.
So what was done? Okay, actually, so here the text used mean value theorem.
And then they use the definition of derivative as.
Yes, yeah.
So where does k come from mathematically? I think we did talk about this, but like from the book's perspective.
Right. So it comes from, it actually discussed in the previous lesson, in defining flux, that you have, where is it?
I think you just passed this.
Okay, yeah, so k times ux is defined to be flux, and I think further down, okay, yeah, this. So here's the definition of flux. It says that this definition assumes that k is constant.
Right.
But now you're letting that constant vary from point to point.
Okay. And so, since it's a function of x,
So regardless of whether you're using a mean value theorem, or as in the book, or using a fundamental theorem of calculus and reverses in the notes, either way you're taking a derivative of something, and k has to be part of that derivative.
okay.
But then if you go back look at that allows you to see where the final result comes from as you look at what's being differentiated here.
Okay. The other thing I had was xz turns to x as change in x goes to 0, right?
That's okay. Still on this problem.
Right.
Okay.
That's what seems to
Okay.
happen.
Yes. So okay, I'm gonna have to explain this. What's done here a little bit further. Okay. Yeah. So here would be the theorem that this is evaluated an unknown point between x and x plus delta x.
Right.
But then because delta x is going to 0, x and xc have to coalesce in one
Right.
point. So yes, it does become x.
Okay.
Oh, there's one thing, I have mentioned this to a couple students who've asked questions about this problem. I want to make sure, make a note to everybody. Let's see where to go. I wonder if anyone's ever done the PDE crossword. But that's an unusual feature of textbooks. Okay. One of the answers in the back of the book for a more recent problem has a mistake in it. Okay. So what we have here, like this term, 4 over pi e to the minus pi squared t sine pi x. Now, if you go to the summation and you set n equals 0, and just look at that term, what do you get? 4 over pi e to the minus pi squared t sine pi x, and then this is evaluates to 1. In other words, this term should not be here because it's already accounted for in the summation. Now, if you change the summation to start at n equals 1, then yes, this term is okay to have. So they basically include this, a valid term twice. All right. Other questions? This problem here that corresponds to the lesson I just covered today, algebraically is a doozy to arrive at this result. So we'll warn you up front about that. Like when you work out the problem using procedure I just described today, and you have an answer that's not necessarily in this form, but it is a solution nonetheless. It's not necessarily obvious that it would get to this in the end. If I recall, my memory may be wrong on this. It's been, well, literally a year since the last time I looked at this problem. There's a lot of algebraic hijinks that is needed to evaluate. You get a solution in integral form because when you're using a Fourier transform, you can always get to a solution in integral form without too much trouble. And sometimes the integral simply can't be evaluated, as I've mentioned, and you have to stop there. So in this case, it is possible to evaluate the integral, doing some things like completing the square and so forth. And, not the sort of thing that I would expect one to do in a test, certainly. Actually, I would not even expect it to be done here, because it's really a sideshow of the problem. What I'm looking for is, do you know how to apply the Fourier transform, solve PDEs? This isn't a class, so it's all about evaluating horrible integrals. So if you're bored of looking for a challenge, then yeah, go for it. And see how it really does work out to this. But for this class, I wouldn't call that the highest priority. So I'm trying to reduce the level of frustration that's bound to ensue from a problem like this. Especially when we have so much software out there for evaluating integrals. Okay, well, I'll stop recording at this point, but certainly I'll hang around in case anyone has questions.